Hello, my name is Ellie White. I'm a student at Marshall University, and I had the great opportunity to work this summer as an RAU for Berkeley SETI Research Center and Breakthrough Listen, also in collaboration with SETI Institute scientists. So I'd like to talk a little bit about the project that I did this summer, working on implementing GNU Radio at the ATA, and kind of what we accomplished. So just to give a little bit of background, the Allen Telescope Array consists of 42 6-meter dishes. And of course, if you listen to Steve Croft, Alex Pollock, and everyone's talk, you'll learn a lot more about it. It's a really amazing instrument. So collaboration between GNU Radio and SETI community really got kickstarted last year with a hackathon hosted at the ATA, which I'm sure many of you attended. So our goal this summer was to implement the basics of GNU Radio at the ATA, a control system, data acquisition system, in order to provide an interface that's kind of user-friendly and also accessible to members of the GNU Radio community and educators, students, and scientists. So mostly what my work consisted of was developing a GRATA module and doing some preliminary tests with some USRPs that have been installed on site. So I'd like to talk a little bit about that. So the module that I developed over the summer is called GRATA. So I had a great time kind of learning how to develop out-of-tree modules for GNU Radio, which I hadn't done before, so that was awesome. But I want to talk a little bit about kind of the blocks that we developed and what they do. So GRATA right now consists of 4 blocks. The control block is kind of the main powerhouse of the group, so it actually does all the work of commanding the ATA antennas to do things. And just a quick note, all of these blocks are built on top as wrappers on top of pre-existing ATA control library code originally written in Python. So the control block initializes the observation, so it does things like setting the frequency, getting the LNAs set up and things like that. It also commands the antennas as to where to go, sends the location information, and also does the deconstruction at the end of an observing run. Does things like stowing the antennas and so on to make sure that the session ends cleanly. So in addition, we have observation blocks. Those are pretty fun. So they basically tell the antennas how to point. So for example, if you want to do a scan where you're just looking at one source for a long time without moving off of it, then you would want to do a track scan. And that block will let you tell the array what to set the center frequency to, and also what antennas to use and the source that you'd like to look at. So similarly, the on-off block is somewhat like the track scan block, but it's a different observing pattern. So instead of just kind of tracking on one source, it tells the array to track on one source for a given duration of time, and then to track on a source slightly offset from the main source, if you'd like to do kind of a comparison there. So the nice thing about the setup is you can actually, if you want to do some kind of observing pattern that's uncommon, like if you want to do, say, a raster map or a DAISY scan, then you can write your own observation block and just connect it to the ATA control block and have it sending like location commands, coordinate commands to the array. And so that makes it nice and customizable. So finally, I'd like to talk about the IF switch block, and that basically just sets the IF switch matrix at the ATA such that the USRPs, which are installed on site, are receiving data from the correct antennas. So now I'd like to talk briefly about data acquisition with the USRPs on site. So there are 2 USRPs currently installed at N320 and N321. So like most radio telescopes, each ATA antenna is capable of observing with 2 polarizations. In addition, each USRP has 2 inputs, so we can currently connect either 2 antennas with both polarizations or 4 antennas with 1 polarization each and collect data streams from there using USRPs. So GNU Radio, thankfully, of course, has a USRP source block, which we can use to interface with the USRP hardware. So on the right, you can see kind of an example of a flow graph that we might use to collect average spectral data. Of course, you can collect raw samples as well if you prefer to store your data that way. So that's kind of state of our USRP system. One quick item of note, USRPs do not form the primary backend for the ATA at this point. However, the system could be expanded with the addition of more USRPs. So it's a pretty exciting experimental system in place. So I'd like to wrap up just by talking a little bit about a pretty exciting detection that I made during the last week of my internship. So it's pretty exciting. So on the left, you can see what is the H1 spectral line in the direction of the source 2350 plus 646, which is in the direction of the galactic plane. And on the right, you can see some data from the lab survey just for comparison. So you can see the data on the left has been basically lined up with respect to the velocity with respect to local standard of rest. So we can compare these two apples to apples. We can see that the spectral line that we detected using the USRP extends from negative 100 kilometers per second to 0 kilometers per second roughly, which really closely agrees with what we see in the lab data here. So that's a really exciting first result. Again, note that the plot on the left has not been bandpass calibrated or flux calibrated as of yet. Very preliminary result, but definitely very exciting and promising for the use of GNU Radio and USRPs at the ATA. So hopefully an exciting future ahead for collaboration between GNU Radio and SETI communities. So really glad, honored that I got to be a part of it. So thank you so much for listening, and take care.